Hello there, welcome back to Life Lessons for Math. As always, I'm your host Wesley, and today we're finally finishing up my first series on calculus. And I apologize for not getting a video. Last week I was just a bit overwhelmed with research in the state of our nation. I was pretty heartbroken and stressed out about it, and just didn't quite feel up to making a video, but I'm back into mostly normal rhythm, so I should be producing videos on the regular again. So with that being said, let's dive into today's video. So we're concluding our first series by talking about, well, Taylor series. And so, I don't know, I liked that little wordplay of like, oh, the end of our series is on mathematical series. And so, I know, I'm ridiculous. But kind of the idea here is, can we write any function as a polynomial? You know, polynomials are some of the nicest mathematical functions out there, if not the nicest mathematical functions out there. And one of the there are a few contributing factors to why polynomials are so nice and why we'd want to write everything as a polynomial. One, it's really easy to take the derivative and antiderivative of polynomials. Remember last video I talked about how finding antiderivatives and therefore area under curves usually requires a lot of artistic skill to actually be able to find the area under the curve because, well, finding antiderivatives is hard. But if everything was just a polynomial, well, finding antiderivatives would be a whole lot easier. And so the ability to write functions as polynomials is really nice for, you know, again, finding derivatives, antiderivatives, all that stuff. Polynomials are also really nice because they're what's known as smooth. Basically, whenever I say smooth within the context of math, what it means is it has infinitely many different derivatives. So why does having infinitely many derivatives mean it's smooth? Well, it's because if you remember in part 2 of the series, I talked about how derivatives don't like sudden change. They don't like sharp change. They don't like it when things abruptly change. They like smooth transitions. And so if something has infinitely many derivatives, that means at no point does a corner or sudden change appear. Whereas if something, let's say, only had 5 derivatives, that means after 5 derivatives something sharp appears, and derivatives don't like sharpness. And so polynomials are smooth, and so it's like, oh, if we could just write something as a smooth function, like that'd be pretty nice. And so there's a lot of different reasons why we'd want to write a function as a polynomial. You know, the ability to approximate something with a polynomial very accurately. So, you know, rather than deal with cosine, I could deal with a polynomial, which is a whole lot nicer than cosine, because nobody likes trig. Well, some people do, but you know what I mean. Okay. So that's kind of the motivating question for today's video, and I want to talk about a little bit about, well, Taylor series and why they matter. Basically, a Taylor series is the answer to that question, right? A Taylor series is what gives you the formula that allows you to write any function as a polynomial. Well, any function. It needs to basically be smooth or have infinitely many derivatives in order for you to write it as a Taylor series. But again, Taylor series just are widely used in like physics and engineering, those kind of more mathematically inclined sciences, because basically a Taylor series allows you, again, to approximate anything with a polynomial, and polynomials are super nice. And so that's kind of the main use outside of math. Within math research, Taylor series are really nice in actually helping us calculate derivatives. Just because in what I do, I deal with stuff that we don't have like rules to take derivatives for. And so what we actually do practically is we do a Taylor series expansion, and then you collect the appropriate terms and you can find the derivative. And so Taylor series are one of the most powerful tools. I know I've said that a lot in this series, but that's why I did the series, is because like everything you learn in Calculus 1 and 2, which is what this series has covered, teaches you incredibly powerful mathematical tools that are used in research level mathematics. And the Taylor series is one of them. It's just like, oh, let's Taylor series that. Let's Taylor series that. We just Taylor series all day long. At least with what I do as an analyst and a PDE person in particular. You know, someone in algebra might not do it, but that's beside the point. Okay, with that being said, I want to motivate a little bit of the life lesson for today before I get into how do they work. Basically, the life lesson is going to come about from how Taylor series are generated. Basically, the more you understand a point and what the function does at a single point. So let's say you have f of x equals sine of x. The more you understand how sine of x behaves at x equals 0, the more you actually understand the entire function. And basically, if you can perfectly understand how sine of x behaves at 0, then you perfectly understand the entire function. Basically, by studying one point, you understand the entire thing. And that's going to be kind of the motivation for the life lesson today, of just like, the more you understand a particular topic, the more you understand how it influences and connects to other things. So like, how does the economy influence education? And how does education influence this, that, or the other? The more you understand education, the more you understand all the things connected to education. And so that's going to be a bit of the life lesson. But with that being said, how do Taylor series work? Well, before I get to that question, I really want to talk about how do series work, because series are really weird. And so what do I mean by a series anyways? What is a mathematical series? Basically, a mathematical series is what happens when you add up infinitely many things. And I touched on this a little bit in my first video on limits, but when you add up infinitely many things, stuff gets weird. And so I want to talk about that today. Okay. So I'm going to start off by talking about a famous series known as, or infamous, more likely, series known as the Harmonic Series. It's infamous because it's one of the worst behaved series around. And yet it exists, which makes all of math more complicated. So the Harmonic Series, I've actually already shown you on this series, is what happens when you take like 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5 plus 1/6 plus blah blah blah. And when you add all that up, you get infinity, despite the fact that you're adding up smaller and smaller things. And eventually you're adding up basically 0, because, you know, when you're like a million terms in, you're like 1/1,000,000. You plug that into your calculator and it's crazy stupid small. Or 1/1,000,000,000. Again, crazy stupid small. So despite the fact that you're adding up basically 0, whenever you add up basically 0 enough times, you get infinity. Again, this is known as a harmonic series. And now that we've seen the summation notation, I'm actually going to write this in the more mathematically compact way. And so before I actually write it in the more mathematically compact way, I want to motivate that a little bit. So we can't ever add up infinitely many things, right? Because we can't even count to infinity. If we can't even count to infinity, how can we add up infinitely many objects? Well, we can't. And so what we do is what's known as a partial sum, is where we start off with. And so this is taking like the first k objects, for instance. And so here, like if I were just to add up these, k would be 6, right? Because I'm adding up the first 6 objects. And remember what this notation means is you plug in 1, so you'd get 1/1, which is 1. Then you go up to 2, plug in 2, so 1/2. Then plug in 3, plus 1/3, plug in 4, so on and so forth until you get to k, until you get to the number that you want to stop at. Okay? And so you do that, and then to actually calculate the series, to actually calculate what happens when you add up infinitely many things, you take the limit as k goes to infinity. And so that's what allows us to actually add up infinitely many things, is again through the power of limits. And so as I've tried to emphasize throughout this first series, everything within calculus is nothing more or less than a limit. And because of that, in my first or second deep dive video, I'm going to talk about the delicacies that come from the fact that everything's a limit, because it actually makes things a little bit delicate whenever you have multiples of these going on at the same time. But that's for another video. And so mathematicians, as I've said before, are fundamentally lazy creatures. We don't like writing more than we have to. And so rather than write the limit of the sum every time, we just write this as the sum as n goes from 1 to infinity of 1 over n. So whenever you see an infinity there, just know that it's really an abusive notation, and it says, hey, I'm adding up infinitely many things through the power of limits. And so just to write that down, we have our harmonic series given by this. It adds up to infinity. Now I want to talk about the alternating harmonic series. And so the alternating harmonic series is what happens whenever basically you allow the signs to change. And so the mathematically compact way of writing this is the sum from n equals 1 to infinity of negative 1 to the n plus 1 over n. And what does that look like? That basically looks like 1 minus 1/2 plus 1/3 minus 1/4 plus 1/5 minus 1/6 plus blah, blah, blah. And so basically by adding and subtracting, we actually get this thing to converge, right? When we make some of the terms negative, this thing actually converges, and what it converges to is the natural log of 2. And the reason it converges to the natural log of 2 is basically from the Taylor series of natural log. And so if you're curious, look up the Taylor series of natural log, make the input be 2, and you'll get out the alternating harmonic series. And I'll get into, again, Taylor series a little bit later, but for now I want to focus on just how weird series can be. And so, you get this alternating series out, and it actually adds up to some specific number, whereas the normal harmonic series just goes up to infinity and blows up. And so because whenever there's negatives involved, it converges, but when it's all positive, it doesn't converge. This is what's known as conditionally convergent. So again, conditionally convergent is what happens when a series converges when there's positives and negatives both involved, and when it's divergent, when it's all positive. So again, conditional convergence one more time. Whenever there's a mixture of positive and negative, it converges, but when it's all positive, it doesn't. And so that's what we see in the alternating harmonic series. And the weird thing about conditionally convergent series, like the alternating harmonic series, is that you can rearrange them and they add up to different numbers. And more than that, you can rearrange it to add up to any number you want to, which is really weird. And let me explain to you why it's really weird. So what is 1 minus 1/2? Well, you can plug that into your calculator, and that's just 0.5. Well, what is minus 1/2 plus 1? So what happens if I switch the order? Well, that's still just 0.5. Whenever you're only looking at finitely many terms, order doesn't matter, right? If I were to add a third to this, it would be whatever that is. And again, like, the order wouldn't matter if I just added a third into it. So at any finite stage, the order doesn't matter, and it'll give you the exact same number out. But whenever you're dealing with a conditionally convergent series, i.e. something that you add up infinitely many numbers with, but it doesn't converge whenever everything's positive, it only converges when there's a mix of positive and negative, you can rearrange it and get any number you want out, which is mind-boggling. It's so weird. It's so unnatural. And so, because of that, the reason I bring up these two series in particular is I wanted to show you just how weird a series can be, just how weird it is when you add up infinitely many objects. Your intuition's just completely tossed out the window, and you have to learn a completely new intuition. And in a normal Calculus 2 course, you would learn how to avoid these types of things. There are basically tests around that tell you when these two things don't happen, tell you when things behave nicely and well and the way you want them to. And that's the part of Calculus 2 that most people don't like, is learning all these tests. But I wanted to motivate for you why those tests are important. Because if you don't have those tests to tell you when things behave well, then you get stuff like this out, where stuff blows up despite the fact that you're adding up super tiny things, or you can rearrange it and get different numbers. And so, does that make sense? So series are very delicate to deal with, and that's why most people don't like dealing with them in Calculus 2, is they're very delicate creatures. But with that being said, let's start moving towards Taylor series. Again, if you want to know if a particular Taylor series behaves well, you would want to apply one of the tests, like the ratio test, root test, something like that, and it would tell you, hey, this behaves well, or probably not. Okay. All that being said, what is a Taylor series? Well, in order to motivate a Taylor series, I want to start off with linear approximations again. So let's say we're looking at some function like this. So we're looking at a function here, and we pick our favorite number, let's say here, right, A. Remember how we would do a linear approximation is we would calculate the tangent line to that number. Right, so we would have our tangent line, and we had a particular formula for our tangent line. Remember what it said is our original function, y equals f of x, is roughly, you plug in your favorite number into your original function, right? So you plug in a to your original, then you plug in a to your derivative, because this tells you the slope of the tangent line, then you multiply times x minus a. And boom, that tells you that your function behaves like the tangent line as long as you're close to a. Okay, so just kind of keep that in the back of your mind. I want to motivate the fact that a second derivative is going to give you a better approximation. So why is this true? Well, basically a second derivative, what would a second derivative be? Well, a second derivative is the derivative of the derivative. In other words, it tells you how the slopes of the tangent lines change over time. So, for instance, if the second derivative is positive, that means that the slopes of the tangent lines are increasing. Kind of going back to what I talked about, what a derivative being positive means. Remember, that means it's increasing. So this tells me that the slopes of the tangent lines are increasing. Well, if the slopes of the tangent lines are increasing, that tells me my function, at least locally, has to look something like this. Because kind of over here, my tangent line is very, very negative. But as I kind of go along, my tangent line gets more and more positive, i.e. it's increasing, right? So here we have a very small but still negative tangent line, and here we have a very positive tangent line, a slope of the tangent line. And so the slopes of our tangent line are increasing, which corresponds to the fact that the second derivative is positive. And notice, what does this kind of look like? What graph does this remind you of? Here, I'll just redraw it. It should kind of remind you of a parabola, right? Well, we have a similar thing. If the second derivative is negative, we get a downward-facing parabola. Okay, so if the second derivative tells us how our graph looks like a parabola, then maybe if we added a quadratic term here, the second derivative would be what tells us the coefficient of that quadratic term. Because remember, a parabola is something like ax squared plus bx plus c, right? We have a quadratic term here, a term raised to the second power. And so, your instinct might be to say, well, let's add in our second derivative, since that's what tells me how it behaves like a parabola, times x minus a squared. And this is almost right. The only thing you have to do is you have to divide by 2 here. So as long as you divide by 2, your function is approximated by this parabola given here. And so you see that, and an actual question might be like, well, would a third derivative give me the cubic term, right? And I would say, good question. Like, that's exactly what your intuition should be telling you right now. So if you add the third derivative in, we're going to have to divide by 6 just basically to make everything balance out. Why do we have to divide by 2 and 6 here? Basically, it comes from power rules for taking derivatives, right? These are just here purely for the power rule to handle that. And so if you don't know what that is, that's okay. That's just the reason they're there. And so the third derivative gives us the cubic term, and so on and so forth. And it turns out if you add up all the derivatives in this form, if you add up all of them, then you get a Taylor series. And notice that the right-hand side is all a polynomial, whereas the left-hand side isn't. And so this is where Taylor series come from. They don't come from the stork or anything, they come from that. No. Terrible, terrible joke, I know. So a Taylor series says that my function is exactly f of a plus, right? We are not dealing with approximately equal to, we're dealing with an exact equality here, f prime of a times x minus a plus, again, the second derivative over a of a over 2 times x minus a squared. And then I'm going to, for the next couple derivatives, I want to motivate this so that I can write down the compact formula. The third derivative, rather than writing 6 down, I'm going to divide by 3 times 2. Right, and it's going to look a little weird, and here I'm going to divide by 2 times 1, and then here I'm going to also divide by 1. And so I'm going to motivate why I'm doing that in a second, but just for the moment, stick with it. And then you would go to the fourth derivative, so this would be 4 derivatives is kind of how we denote that. And this would be 4 times 3 times 2 times 1 times x minus a to the fourth. And then you just keep that pattern going. You add up all of those, that exactly gives you your function. And so what's up with these denominators? Like, what's going on here? Again, they're there to deal with the power rule, but we can write these in a compact notation using something called a factorial. So, for instance, 4 factorial. So we denote a factorial with an exclamation mark. 4 factorial would be 4 times 3 times 2 times 1. So this is exactly 4 factorial. And again, kind of following that pattern, this would exactly be 3 factorial. Basically what a factorial does is you start at the number that it's given, so 4, you subtract 1 multiply, so times 3, subtract 1 multiply, so times 2, subtract 1 multiply times 1, and you do that all the way down to 1. You don't go towards 0 because then, well, everything times 0 is just 0. So you stop at 1. And again, 6 factorial would behave the same way. You start at 6, multiply times 5, times 4, times blah, blah, blah. Right? You just keep on going all the way down to 1. Okay, so with that being said, just kind of that notation out of the way, the compact version of the Taylor series says that f of x is equal to the sum from 0 to infinity of the nth derivative evaluated at your favorite number. So again, we're treating the idea that the 0th derivative is just my original function. Then you plug in 1, my first derivative is, well, my first derivative, etc., etc. Then you divide by n factorial. Notice that this kind of corresponds to that at every time. So you'd have 2, 3, again, 4, they match. And then you have times x minus a to the n. Okay, so this is the Taylor series representation of a function, and it's what allows us to say that a function is a polynomial. At least an infinitely large polynomial. There are some small caveats, some small assumptions that I'm making though. Again, I'm assuming that I can take derivatives. Remember, derivatives, you can't always find them because they don't like sharp corners. So I'm implicitly assuming I'm dealing with a smooth function because I'm implicitly assuming that all these derivatives exist. Right? So basically you can only actually write smooth functions as polynomials, but for the most part, we only really care about smooth functions. And there are ways to avoid smooth functions because we can actually weaken our notion of a derivative again, which I'll talk about eventually. Okay, so with this being said, I want to give a couple of examples and then kind of transition, start to wind down a little bit. So sine of x, you can actually write as x minus 1 over 3 factorial x cubed plus 1 over 5 factorial x to the 5th minus 1 over 7 factorial x to the 7th, so plus blah blah blah. So what's kind of the pattern here? The sign is alternating, and then you're just looking at basically kind of the odd powers of x. And so through this, rather than deal with sign, I can deal with a polynomial. E to the x is another kind of popular one. Basically, e to the x is 1 plus x plus 1 over 2 factorial x squared plus 1 over 3 factorial x cubed plus 1 over 4 factorial x to the 4th plus blah blah blah. Right? You add all that up, you get e to the x. So rather than deal with exponential functions, we can again just deal with polynomials. And so everything's nice and pretty and perfect because it's a polynomial. But why? Again, I've motivated this a little bit, but basically you can approximate your highly nonlinear thing with a nonlinearity that's easier to understand, right? Because sine of x and e to the x are nonlinear, not even close. And so you can approximate it with something that it's easier to understand x cubed and x to the 5th for most of the time than it is to actually understand sine of x. And so just to kind of give a little bit of understanding as to how that works, and also to start motivating the life lesson a little bit, let's look at how this works for sine of x. Right, so let's say we're looking at the graph of sine, which looks something like this, right? Kind of repeats itself on and on forever in both directions. Okay, now just to kind of refresh the formula I just erased of sine of x is x minus 1/3 x cubed, or 1 over 3 factorial, my bad, 1 over 5 factorial x to the 5th, etc., etc. All right, you just kind of keep the pattern going. Okay, so if I don't want a very good approximation to my function, if I just care about a first order linear approximation, I would just kind of cover up everything else and look at x. So sine of x is basically x, so what's the graph of x look like? The graph of x looks something like this. So notice that close to 0, x and sine of x are basically indistinguishable from each other. But if you get very far away, they're not that close. And so just understanding that first derivative doesn't really help me understand much away from my original point that I considered. But if I go to the next order, if I go to the cubic order, what's going to happen is I'm going to basically get something out that looks like this. And so notice that I get a much better approximation for a longer time. So it's much closer to sine of x further away from 0. So I can go out a little bit further and get a better approximation. So if I'm not very close to 0, but I still want to approximate it with a polynomial, I'd want to at least use a third order approximation. And then you can kind of keep going with this idea of like, okay, let's go to 5th order. So what's going to happen is you're going to get something that looks like this out. So again, you're able to go even further away from the origin and still have a decent approximation. You know, you can go further away from your favorite point and still be relatively close. And so the further and further out you go, the more and more you actually understand the entire picture. Does that make sense? And so this is what kind of motivates the life lesson. And so just before I do that, I want to kind of refresh our mind on the Taylor series formula. Remember, it's f of a plus f prime of a times x minus a plus f double prime of a over 2 times x minus a squared, L2 factorial, plus blah, 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 right? You just keep going, add up the other derivatives. And so kind of putting all this together, notice that the more I understand how my function behaves at my favorite number, the better my approximation is, right? Because that's what leads to these coefficients in front of x cubed, x to the fifth. It's information about how my function behaves at the origin in this case, but at my favorite number in general. So it's like, okay, your constant term is just, well, what is my function at my favorite number? Then what is the slope of my tangent line at my favorite number? Then what is the concavity? You know, like, does it look like a parabola up or down at my favorite number? And so on and so forth. And you put all that together, and each additional piece of information that you have gives you a much better and better approximation. And so, again, this is what leads into the life lesson. Think about something where you can start to try to understand that one issue, and the more you understand that one issue, the more you understand what underlies that issue, what leads into it, what enforces it, what affects it, and what does it affect. So basically, you know, you have your issue, so what is the input of that issue and what is the output of that issue? How does it connect with everything around it? So for instance, education. You know, like, education is influenced by the economy. It's influenced by the job market. Especially like at the college level, if there's a poor job market, you know, it will affect whether or not people decide to go to college. And, well, whether or not people go to college affects the economy. It's all connected, and the more you dig into how education works, the more you understand all the influences, that's the word I was looking for earlier, all the influences on education and how education influences the world. Does that make sense? And so, you know, whether it's the racial injustice and systemic racism issue, you know, just digging into that and starting to understand what all feeds into this, what all influences systemic racism, why is this a problem? And then starting to understand, well, what all problems does it create? The more you understand and look at systemic racism, the more you understand how the roots go into and pervade society. And not just systemic racism, again, education, the economy, whatever issue it is you want to study, I would encourage you to just like really lean into it and look at how does understanding that issue actually help me understand everything connected to that issue. Does that make sense? I hope that makes sense, and I hope that's encouraging of like, okay, I just need to dig into this, and the more I dig into it, the more I'll understand it, and the more I'll understand everything surrounding it, how it connects to the rest of our society and our culture. So, with that being said, that's kind of the end of today's video. So what's next on the channel? So I have a couple things that I'm wanting to talk about. So next I want to probably in this main series talk about differential equations. I want to start transitioning into more of a research level conversation. But I also am going to have some deep dives talking about differential operators and talking about how limits behave when there are a lot of them going on. So like, what happens when you have integrals and derivatives and sum and series all going on at the same time, because all of those things involve limits. How do they play with each other? That's kind of a complicated issue, so that'll be one of my deep dives. So I'll have kind of a deep dive series, and I'll have kind of the main series where we start plowing into differential equations. And then I also want to maybe have some shorter videos where I just talk about what math is to me. What does math research look like, that kind of stuff. And so if you're interested in any of those series, those are the 3 that are kind of percolating in my mind. So let me know your thoughts on those in the comment section down below. And I'll start, writing the videos for them and just continue to let them marinate in my mind, if that makes sense. So again, those are kind of my 3 options that I'm thinking about. With that being said, guys, I hope you have a wonderful day, and I will catch you in another life. Bye.